Hello and welcome to Beamer Folk.
Before we get on to me applying the Wheatstone Bridge, I thought I would demonstrate my Phono preamplifier that I designed and built 10 years ago. So what I'm going to do is basically demonstrate the performance of my existing Phono preamplifier. So I start off with this. I've now produced an inverted RIAA network on a printed circuit board. Well, in fact, it's a strip board actually. Moving over, we have my existing Phono preamplifier. In front of that is my DDS oscillator, and that was the subject of another video. And over here on the top left hand corner is a power pack, and that's driving the DDS, and it's going via a filter network. You don't strictly need that, but it does improve the situation, and that was the subject of another video. For those that don't know, the reason why we have an RIAA circuit at all in this system is to ensure that when placing an audio signal on a thin piece of plastic media, to pack in the maximum amount of audio information on the smallest surface area, they needed to crush down, as it were, the bass signal, so that the needle at the studio, at the manufacturer of the record, the needle doesn't impinge, damage the adjacent groove. Of course, we all know that there really is just one groove on the disc, but I think you follow my thought there, and that is that what they needed to do was squash down the lower frequencies so that the needle effectively didn't push the plastic into the next groove, so that we can establish on a piece of plastic, vinyl, an audio signal in stereo that didn't damage the structure of the disc itself, and therefore pack in as much audio information on a record as possible. And of course, if you condition the audio signal on the disc, you need to decondition the signal when you play it back on your home hi-fi system. So that's the reason why we have an inverter, which effectively would reside in the manufacturer of the record, so that contours the audio signal. And I've only got one channel here. For stereo you would naturally need two, so that would contour the audio signal onto the disc. Well, this is the sine wave signal output from my DDS, 1 volt peak to peak, going through the inverse RIAA and into my 10-year-old RIA preamp. And what you're looking at now is the output, and as you can see, it's a perfect sine wave, and the amplitude is, well, it's 1 volt per division, so we're looking at 1, 2, 3, 4 volts. The input to my RIAA preamplifier is 30 millivolts peak to peak. So you can see that there is a lot of gain in a RIA preamplifier. And when I just show you the signal on the input to that preamplifier, and as I say, it's 30 millivolts peak to peak. And you can see, let me increase the brilliance, you can see that it is actually quite fuzzy because of the very low signal, but you're looking at about 1, 2, 3 divisions, which represents at 10 millivolts per division, 30 millivolts peak to peak, and that translates into a gain of 133.3 reoccurring, which represents 42.5 dBV gain. So it's quite a gainful device. And I'll just switch back to the output of the preamp, and what I'll do now is I'll load up the output to actually see whether we have any amplitude movement, and I'm going to do that now. I've got a 4K7 resistor and I'm putting it now on the output, and I'm switching it backwards and forwards, so you can see there is a very small amount of drop there, and I tell you why that is. And that is on the output of the op-amp within my preamplifier. I have a 200 ohm resistor to defend the op-amp from larger capacitive loads. So as there are two series resistors there, you would expect a little amount of drop. Well, that was the sine wave demonstration. I now go over to demonstrating the virtues of a square wave in this analog world. In respect to the previous sine wave demonstration, I failed to mention that the frequency was spot on 1 kilohertz. That was important. And the next thing was that you need an oscillator. I'm using this DDS, but you need an oscillator to drive a fairly low impedance. And the reason being is that the inverse RIAA equalizer at high frequencies, say 20 kilohertz, you're looking at a load of approximately 1k ohm, that's 1000 ohms. Some oscillators may not be happy with that kind of load. The oscillator that I built seems to be happy with that load, but some might not be. Okay, well, I get back to this square wave. Now, I've opened the square wave up a bit, but it still represents 1 kilohertz. And why is a square wave so important to the function of a phono preamplifier? It's simply because it shows up the failings and successes of the circuitry. Now, what you're looking for is in each corner of this square wave, you're looking ideally for an absolute 90-degree bend. That is, the rise time here is sharp, it gets to the top here, and there should be a really nice flat 90-degree bend. And that's equally true of the falling edge corner here. That has to be 90 degrees. In the corner here at the bottom, 90 degrees. And the rising edge at the bottom here, 90 degrees. If there's any failing, you will see a tendency to produce a differentiated waveform as opposed to a square waveform. Or indeed, if the capacitance or the equalizer is not functioning correctly, you'll get a rounding of these flats. So it'll start to look as though it's trying to make a sine wave. But ideally, this representation of both my old RIAA preamplifier and the small inverted RIAA circuitry, passive circuitry, the equalizer, are in pretty good harmony and are working perfectly. If you study this carefully, you can see that there is a very slight slope going down here. And I've got my oscilloscope on the DC position. And likewise, on the top of this square wave, there's a very slight incline. And that is telling me that the bass response of my phono preamplifier, or indeed the inverted, is slightly lacking in lower frequencies. This is a minuscule amount, but that could be due to aging capacitors within my RIAA preamplifier. It could be significant of that. But if there were really bad things going on, the shape of this would be pretty gross looking by comparison with what you're seeing before you. The rise time is important as well, so this is another aspect of a square wave. The rise time is important. The rise and fall time here represents 8 microseconds. Well, that is not, in a digital world, that is not fast at all, but in an audio world it is. And if we just, I'll get my calculator. If we go 8 microseconds and find the reciprocal of that, it comes out at 125 kilohertz. Well, for an audio signal, that is a significant frequency. The preamplifier I've built goes to about 22 kilohertz, but you can see this has got quite a good rise and fall time for an audio piece of equipment. Given the importance of a square wave, bear in mind that you could make an oscillator to drive this equalizing system using a simple Ni 555, 555, the ubiquitous chip. And at 1 kilohertz, if you got that adjusted to 1 kilohertz, you could see all that's going on here. You don't really need a very expensive oscillator to demonstrate this. You can, of course, reduce the frequency of the oscillator, and it will show more and more emphasis, if you like, zooming in on the lower frequency responses. And of course, if you were to increase the frequency from 1 kilohertz, that would show the higher frequency responses. But bear in mind, a square wave at higher frequencies, you would have to have a very good circuit to display all the harmonics. Okay, so what I've done is on my DDS, I've managed to program in a sweep function, which is useful for this type of audio work. There's a slight disadvantage in the sense that it is not a linear progression or logarithmic linear progression of the frequency. The nature of a DDS means that there is a step change, so that what you'll see is a stepped change sweep function of this oscillator, and I just put that into that mode now. There we are, and it's sweeping now from about 5 hertz to 22 kilohertz in a logarithmic fashion. For this sweep function, please bear in mind that the switching nature of both the camera and oscilloscope at times produces flickering and flashing on the image that you see. But I now put my DDS into sweep mode, and let's see how we get on. You won't be able to actually see the frequencies because my counter will not catch up with the changing of frequencies, and you will hear me flicking through the oscilloscope to keep up with the sweep itself. The thing to concentrate on is the amplitude of the signal here. We've got 4 volts here peak to peak, and what should happen is between the lowest frequency, which on my sweep is 5 hertz, and the highest frequency, which I think is 22 kilohertz, you should not see any appreciable difference in amplitude, and this is measuring the output of my RAAA preamplifier. So now all I've got to do is actually put it into sweep mode. There we are. Now you can see it's running at low frequencies, and the frequency is increasing and increasing. At the moment we're at 50 hertz, 60 hertz, up to 150 hertz, 250 hertz, 400 hertz, 600 hertz, 1000 hertz, 2000 hertz, 3000 hertz, 5000 hertz, 8000 hertz, 11,000, 15,000 hertz, 18, and there we are, 22 kilohertz. Now let me just put that back a bit. Here we are at 22 kilohertz on the output of my RAA preamplifier, and as you can see, there isn't a, let me use the proper end of this pointer, there isn't any appreciable drop in amplitude, which is a good thing. I'll just run through that one more time to, let me put the oscilloscope back to there, and then one more time I'll go through a sweep. There we are, we're looking at 5 hertz, 13, 20 hertz, 30 hertz, 50 hertz, 100 hertz, 200 hertz, 300 hertz, 500 hertz, 1000 hertz, 1500 hertz, 2000 hertz, 4000 hertz, 6000 hertz, 8000 hertz, 10,000 hertz, 13, 15, 15,000 hertz, and then 22. So I'm happy with that. And of course the other channel works exactly the same as this. Well, as the Phono Preamplifier actually has 2 channels, I can assure you that the second channel is working identical to the first one. And in fact, actually I've been testing it on the right hand channel, but the left hand channel is working identically. So why do I need to update my Phono Preamplifier? What's actually wrong with it? Well, there are 2 things. One is that very, very occasionally I get a, I can only describe as a noise like on one channel. And the other reason is that because I'm living fairly near a repeater transmitter station, I'm getting breakthrough on the input. So the first fault, the first problem, that I'm experiencing very rarely, I strongly suspect due to the fact that I've used non-polarized capacitors, particularly in one critical location. And so what I wanted to do was replace these rather inexpensive non-polarized capacitors with quality Nichicon Muse non-polarized capacitors and see whether that'll cure the problem. I suspect the old electrolytics, one of them was starting to leak very, very slightly and randomly due to old age. And I wanted to put some work into the front end, which I have done over the past, but I wanted to redesign the front end slightly so that it becomes more RF immune. So those are the 2 faults that I wanted to address. In respect of the testing, the appraisal of my old Phono Preamplifier, it's probably worth mentioning that this was a fairly scant affair, just a basic assessment of the unit. You can actually go into great depth into the analysis of a Phono Preamplifier. Secondly, when we looked at the sweep function sine wave at 22 kilohertz, I did actually notice a slight drop at the very high frequencies, somewhere between 18 and 22. And the reason for that is that I have been experimenting to eliminate the RF breakthrough, as I've mentioned. And one of the things I did was to try and pull down, cut off sharply at the very high frequencies to see if that would help. It didn't, as it so happens, which is another reason why I wanted to update and modify, my Phono Preamplifier. And so to the inverse RIAA circuit that I've designed and built. You can see that
I established this on a strip board. I've made a video regarding the basic construction of a strip board that I'll link above. Now, all resistors and capacitors are 1%. You can see here the number of resistors up here, and you can see the strip board isolation holes here. You can see the capacitors here, and I've got it marked as a 10 nanofarad, and that is correct. There are two capacitors here to make 10 nanofarad. If you've got a box of 10 nanofarads, you would actually choose just one capacitor. It's absolutely spot on via the Wheatstone Bridge. Absolutely spot on, a 10 nanofarad. Well, I didn't actually have one, but I had one that was slightly short of 10 nanofarads, and I used a very small padding capacitor here with a few picofarads that made it spot on to 10 nanofarads. And that's how I work. I construct my capacitors, my precision capacitors. The next group of capacitors here are the 36.3 nanofarad, where you can make this up using two parallel capacitors of precisely 33 nanofarad and 3.3 nanofarad capacitors parallel. So that would be two capacitors. But as you can see here, I've made them up of four. And what they are is 10 nanofarad, 10 nanofarad, 10 nanofarad. Well, that brings me to 30 nanofarad. And I used a 4.7. Well, that would come to 34.7. That's not exactly 36.3, is it? But of course, all these capacitors are slightly high of their value. And all I did was combined four capacitors until I hit spot on, via the Wheatstone Bridge, 36.3 nanofarad. But if you go out and purchase capacitors, it's probably convenient to just buy precision 1%, 30 nanofarad and a 3.3 nanofarad, and parallel them together. Now let's explain that. There's one other bit here. I've isolated input and output. As you've noticed here, the input is on this rail here with an isolator hole here. The next rail here is 0 volts all the way across, and the next rail is the output. So the output to input is isolated via a 0 volts. That was part of the design. So going to the circuit diagram here, you've got on the input 1 volt AC RMS on the input, going through this network here through to an output with R4 of 68 ohms, which will produce a 10.6 millivolt. This is approximately, I don't really have the equipment to measure this accurately, but 10.6 millivolts RMS, or 30 millivolts peak to peak on the output. So as you can see, there's a fair degree of reduction across this equalizing inverse RIAA network. At high frequencies, this network here, the 36.3 nanofarad, the R and the C's, are virtually a short circuit. So the only network that high frequencies can see is this resistor, this network here, that equalization network here, and the resistor on the output. At low frequencies, this resistor is seen, that resistor is seen. There's hardly an effect with the 10 nanofarads. And then you see the network of the 36.3 nanofarad. And of course the 68 ohm resistor there. So you can see that the frequencies are split, but it's not a split change. It actually is a kind of linear progression. And the first network here, the 10 nanofarad, is conditioned to be exactly 75 microseconds. So if you multiply the 7.5 k ohm with the 10 nanofarad, you come out with 75 microseconds. And if you look at the lower frequency network here, the R is a construction of these four resistors, and it's 87.6, odd value number, I know, but you can adjust resistors much easier than keep buying stocks of capacitors. And then you've got, as I mentioned above, the construction of my 36.3 nanofarad using 4 capacitors, as I mentioned here. That's 3 high reading 10 nanofarads and 1 high reading 4.7 nanofarad. That's how I've made it. So you would think this is perfect. The only issue that there is with this is that one network here, which is a lower frequency network, kind of interferes very slightly with the high frequency network. This is a very well established system, structure, circuit, very well used. And the high frequency network very slightly interferes with a low frequency network here. And if you come down to this little formula here, you've got 7.5, well that's that, in parallel with the 87.6K, which is here, multiplied by 10 nanofarad, which is the capacitance here, plus the 36.3 nanofarad capacitor. And if you multiply that up, you come to 319.9 microseconds. Well, it should be, theoretically, exactly on 318 microseconds. So there's a very slight difference there. And that difference is caused by the interference between all these components being soldered next to each other. I needed to mention 2 additional things. One is I needed to be clearer about the timing networks of these components. One is that this network here should represent 75 microseconds, and it does. This network here, the R and the C, should have a timing of 3.18 milliseconds, and it does. Both of those are spot on. It's only the combination between the 2 networks that produces a very minor error, and that of course is the 318 microseconds, 318 microseconds, which in practice came out to be 319.9, well it's 320 microseconds. So there's a 2 microsecond difference there. The other thing that I needed to mention is R1. Truly, R1 is 267 ohms. You have to take into, and it's critical, you have to take into consideration the source impedance of your oscillator. And my oscillator is a DDS oscillator and has an output impedance, literally a series resistor of 47 ohms. So this circuit works ideally with, if you add those 2 together, R1 and the source impedance of 47 ohms, you come to 267 ohms. Well, if you've got a 300 ohm output impedance oscillator, you can remove R1 and just have a link there, and the source impedance would be then 300 ohms, which is not a million miles away from 220. And you could, with a resistor, make it to 267. But when I operated this circuit, the performance is not greatly different. You could have a 50 ohm source impedance. That wouldn't make a great deal of difference, would it? That would come out at 270. I thought it was about time we did a little bit of Wheatstone bridging. Before us we have AC millivolt meter, cheapo meter set to minimum AC range of 6 volts, full scale deflection. That's an analog description, isn't it? Here we have the Wheatstone bridge that I've constructed. I'll come back to that in a second. The DDS oscillator set to a sine wave of 1 kilohertz at 1 volt RMS, and of course the power pack. Now what I've got here is a pack of about 10 nanofarad capacitors. So I thought those were the capacitors I would test. So one side of the bridge, which is this side here, is conditioned for 10 nanofarad, and its reactance for a 10 nanofarad is 15.915 k-ohm. Over here I have my reference capacitors. They are 4.65
nanofarad each. I've got two of them in parallel. That comes to 9.3 nanofarad. So not quite 10 nanofarad, which is the other side. And we've explained that you can do this. It's fairly close, but it's not 10 nanofarad. And the reactance for that capacitor assembly is 17.114 k-ohm. Okay, well, if you look at the AC millivolt meter, it's in a kind of null position, but in AC that's not quite right. It only goes to 0, it doesn't go to negative or positive, so, and it's reading 0.7 of a volt RMS. Now I've got a little batch of 10 nanofarad mylar film capacitors here. I think there's about 10 of them, and what we're looking for is an absolute 0 on the meter. If it's anything else, the capacitance could either be higher or lower, as I've mentioned before in the video. And you can't, with this system, exactly know without adding a small amount of capacitance whether the capacitor is under value or slightly over value. So what we're looking for now is absolute 0. As soon as we hit absolute 0, we know it's the same value as the calculated 10 nanofarad of this 9.3 nanofarad reference capacitor. So let me open these up now and we'll see what we've got. Hopefully this will work for me. I haven't got the circuit on a printed circuit board, have I? A strip board, and it's on a breadboard, but we'll see how we go. And I'll reject the ones that are not 0. So put that into position, and what have we got? 12. Well, that's fairly close, but not what we're after. So I put that to one side. 0, 1, that's pretty good, isn't it? That's pretty spot on. But we might be able to do a bit better. So I put that slightly positive of where I want to place zeros. That's absolute 0. So that's a thumbs up. See, once you get going, it's quite an easy process. You can do these quite quickly. What have we got there? 0 again. Well, that's spot on. Let's move that into a spot on position. Go to another one. Ooh, I've just dropped one on the floor. Let's just go. Well, that's a 10. That's not so good. I'll reject that. Another 0. We've got 3 absolute zeros at the moment and 3 that are not. Another one. There's always a mixture of values in any batch, and some batches have been already cherry-picked so that the whole batch will be either a surplus of capacitance or a deficit of capacitance. That's got a 7 in it, so that's 7 millivolts, so that's rejected. Got a 16 in there, so that's rejected. Got a 6, yeah, that's rejected. And finally, and that's a 5, I'll reject that. So out of that demonstration, we've got exactly 1, 2, 3, 4, 5 absolute 10 nanofarad capacitors. And you could use those in a phono preamplifier or anything else that requires a precision capacitor of value. There are other aspects of precision, but I'm looking at here today just the capacitance value. And I've got out of, 12 capacitors, I've got 5, so just under half. For a bit of fun, I thought I would construct a 10 nanofarad capacitor using this setup. And what I've got is a couple of 4.7 nanofarad mylar capacitors. And let's have a look at the AC millivolt meter and just see how I can do this. Now, first of all, let me see. I've got to fit this in because I'm paralleling these capacitors. What do we got? Now we come down to about half. Okay, so it's seeing that 4.7 nanofarad. So what I'm looking for, what I'm trying to make, is a 10 nanofarad. And I'll parallel in another 4.7. Now we've got two of them, and we've got two little ducts, 22. So now I've got a ceramic little capacitor of what value? Could be 47 puff. I don't know. I think it's probably 470. Now let's see if that does the trick. Bang. There we are. Another thumbs up. So you can see how I constructed that 10 nanofarad out of effectively 3 capacitors. I thought I would just add the resistive values which were in series with each capacitor to construct the Wheatstone Bridge. I made the 10 nanofarad reactance resistor out of an assembly of 22k in parallel with 56k plus a series resistor of 120 ohms, and that comes out at 15.915 ohms. The 9.3, which is the assembly of the reference capacitor, 2 capacitors, which came to 9.3 nanofarad, I constructed out of 22k in parallel with 68k plus a 470 ohm resistor plus a 22 ohm resistor. In total, that's 4 resistors, and that comes to 17.114 k ohm. There are online facilities for paralleling capacitors. I'm old-fashioned. I used a calculator to construct this, but you can very quickly go through values.
This is Beamer signing out for now.